So we've now covered what to do when trying to model measurement data that might be log normally distributed. We've covered what to do with count data that might be Poisson distributed. And now we're going to talk about presence-absence data or proportion data, which are often binomially distributed. To do this, let's call up our trusty ArcData package once again. And specifically, let's pull up the Nelson data set. This is a data set of pottery types and counts from an archaeological site in New Mexico, I believe. A guy named Nelson excavated the site. And this site is a Pueblo San Cristobal, with 10 different stratigraphic layers, each one 1 foot in depth, because it's old school before the metric system made its way into American archaeology. And so with this Nelson data set, right, we can use the view function or click on it here in our environment and see what we've got. We've got these 10 rows for depths, and we've got different types of pottery: corrugated, biscuit, type 1, type 2, various types of 2, and then type 3. Type 1, Type 2, and Type 3 are referring to how many colors they have on the glazed ware, I think, of the pottery sherd. And so what we want to do, right, is model presence or absence of a certain pottery type through each of the stratigraphic layers. Let's say Type 3 is what we want to do. And now if we look at Nelson Type 3, we run that, we can see that there's 10 different values, but they're counts of type 3 pottery, 5, 6, 3, 0, 0, 1, 0, 0, 0, 0. We're not really interested in the counts, right? If we were modeling counts, that would be a Poisson GLM. What we're interested in is kind of the presence-absence of this type 3 pottery. Right? For each stratigraphic layer that we've got, what's the probability of recovering a piece of type 3 pottery? And so in order to translate kind of our counts of type 3 pottery into just zeros and ones, presence and absence, we're going to use a function from the dplyr package. So load the dplyr package using the library function if you haven't already got it in. And we're going to add a new column to the Nelson data frame. I'm going to call it PA for presence absence. And the function from dplyr that we're going to use is called case when. And let me write the function out, and then I'll explain to you what it's doing. So we've got Nelson type 3 greater than 0, tilde 1, comma, Nelson type 3 equals 0, tilde 0. So what this case when function from the dplyr package is doing is saying, all right, when Nelson type 3, when the value of that column for any specific row is greater than 0, I want to give that a value of 1 and assign that to this new column that we've got called Nelson $PA, presence absence. So when type 3 column is greater than 0, give it a 1. When the type 3 column is equal to 0, give it a 0. And so you'll see when I run this that if I were to then look at this Nelson data, the type 3 column here at the very end, right, that has the counts that were originally there, 5, 6, 3, 0, 0. What we then did is use that case when function to say, all right, instead of a 5, make it a 1. Instead of a 6, make it a 1. A 3 becomes a 1, and zeros stay 0. So now we have this PA column at the end with just presence or absence, zeros and ones, which is really a neat way to do that using this case when function and this kind of logical operation of whether type 3 is greater than 0. And so now that we've got our Nelson PA data, we want to plot this. PA is a function of depth data equals Nelson, just to take a look at what we've got going on here. You'll see that because it's all zeros and ones, right, our plot, the y-axis PA variable, takes values of 0 or 1. And then depth, we've got 10 different depth measurements, each one 1 foot deep. And it looks like all of the type 3, or at least more type 3 pottery was found at lower depths, kind of depths 1, 2, 3, 4, 5, maybe up to 6 feet deep. And then from like 4 to 10 feet deep is when you're more likely to find no type 3 pottery. And this plot here should really help to illustrate why it is that we need a generalized linear model, right? Because when we think about proportions or percentages, which are just proportions times 100, or when we think about presence-absence data, zeros and ones, those don't meet the assumptions of a Gaussian linear model like we talked about in the beginning. It's the same deal as with Poisson data, that assumption 1, first of all, that the model makes sense. Let's just plot a linear model here of PA as a function of depth for the Nelson data. Look at that nice model fit there. Straight line. If I were to extend the plotting window here, that line would just keep going in a positive and negative direction. And so if we were to, all right, let's extend the x limit from C out to like 15, maybe. And let's extend the y lim down to negative 1 to 1. So if we plot our data there and now plot this line, look at this. If we were to keep digging at this Pueblo site down to a depth of 15 feet deep, our model is predicting that there is a negative 0.75 chance, a negative 75% chance of finding type 3 pottery. It just doesn't make any sense, right? This model's predicting unrealistic values. And so we need to come up with a way to accommodate that, and a GLM is the way to do that, right? So model, the assumption 1 of a Gaussian linear model is violated. This doesn't make any sense. We need to do something about it. And of course, because we're dealing with binomially distributed data, in this case, these presence-absence data, they only take values of 0 and 1, and not much in between. And so it becomes kind of difficult to talk about normal distribution of these values when they're kind of taking, they're not necessarily continuous distributed data, right? These are bounded by 0 and 1. These are discrete data, and so pretending that they're normally distributed might not always really work out that well. This is why it's just better, right off the bat, to use a generalized linear model and actually specify that we're dealing with a binomial family model in this case.